All right, welcome back to the Chem 12A lecture videos. Of course, I am Dr. Pitcher, and we're going to be starting Chapter 7, which is an introduction to alkenes, in particular their structure and reactivity. Now, in this chapter, I want to start off with a brief intro to alkenes. I'll talk about the idea of, or the concept of, degrees of unsaturation and how to calculate degrees of unsaturation. Then we'll look at alkene nomenclature, including cis-trans isomerism, which we've talked about before, but we'll talk about it again. And then lastly, alkene stereochemistry and a particular type of designation or nomenclature called the E and Z designation. So, what are alkenes? So alkenes are hydrocarbons containing double bonds. So hydrocarbons meaning all hydrogen and carbon. And double bonds, we have some carbon-carbon double bonds. So some examples here. And these are just a few alkenes. Now, I want to call your attention to some of them. We have these first two are just regular straight chain alkenes. We could have branches on some of these, so we'll worry about that later when we worry about nomenclature. I've got one here with the double bond on the end. We would call that a terminal alkene. This is an internal alkene. If we have more than one double bond, we would call it a polyene. And this one here is a diene. And this is a triene. Now this diene happens to be conjugated, which means that we have alternating double and single bonds. This triene is also conjugated. This diene here is what we call isolated. There's an extra carbon in between the two double bonds. So it goes double bond, double bond. As opposed to the conjugated diene, which is double bond, single bond, double bond. And then if we have double bonds back to back, so just double bond with a carbon in between, and that's the dot there is a carbon, we call this cumulated. That would be a cumulated double bond, or cumulated double bonds. Accumulated alkene, accumulated diene, I should say. And then here we've got a couple examples of cyclohexene, so a cyclic alkene, one of which I put a substituent on. So these are just some examples. The text does talk a little bit about some of the industrial production of alkenes, but you really don't need to worry about that. All right, so let's take a look then at some degrees of unsaturation. All right. So let's take, for example, the following alkane. So this is pentane, and it has a formula of C5H12, which is the general formula CnH2n plus 2. And this is what we call saturated. That is to say, it is saturated with hydrogen. We have as much hydrogen as we can attached to carbon in this molecule. Let's take a look at another example. This is 1-pentene, and again, we'll talk about nomenclature a little later. Let's look at its formula. 1, 2, 3, 4, 5 carbons. So C5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C5H10 hydrogens. So this is of the general form CnH2n. And this is unsaturated. And so unsaturated means that it's not saturated. We have a certain amount of, we're a little bit, we have a little less hydrogen than we would if it was saturated. In particular, this one has 1 degree of unsaturation. Let's look at a different, let's go ahead and look at 1,3-pentadiene. And this has the formula C5H8, which is CnH2n minus 2. This is also unsaturated. We have 2 degrees of unsaturation. Now there's some other interesting things here. We could take a look at cyclopentane, which is an alkane, but what's its formula? C5H10, 2, 4, 6, 8, 10 hydrogens. So again, 1 degree unsaturation. And let's look at 1, 2, 3. So carbon there with the hydrogen. You know, let me draw this out a little bit better. Sorry. Let's do this. H, C, 1, 2, 3, C, CH2, CH2, CH3. This is 1-pentyne, which is also C5H8, and is 2 degrees of unsaturation. So for every 2 hydrogens less than saturated, we'll get 1 degree of unsaturation. Okay, so again, for every 2 hydrogens less, so if we have sorry, I'm just looking for another pen here. My pen is running out. So if we have CnH2n, so instead of CnH2n plus 2, we're going to have 1 degree of unsaturation. So for 5 carbons, we would expect there to be 12 hydrogens if it's saturated. So if we only have 10, that's 1 degree of unsaturation. If we only have 8, we're short by 2 pairs of hydrogens, so 2 times 2. So that's 2 degrees of unsaturation. Each degree of unsaturation represents a multiple bond or a ring. I should say not represents, but corresponds. And really I should say a double bond, but I'm going to say multiple bond because if you had 2 degrees of unsaturation, that could be accounted for by a triple bond. So a ring or a single bond, excuse me, a single double bond, a ring or one double bond gives you 1 degree of unsaturation. To get 2 degrees of unsaturation, you would need 2 double bonds, or a double bond and a ring, or 2 rings, or 1 triple bond. And so you could see something like, let's draw here, benzene. Here we have 1, 2, 3 double bonds and a ring, so that should be 4 degrees unsaturation. And indeed, C6H6, normally we would have C6H14 is the saturated. Let's scoot this up a little there. So I could look at how many saturated hydrogens I should have, 14. I can subtract how many I actually have, 6, and then divide that by 2, and that's going to give me, so 14 minus 6 is 8, divided by 2 equals 4. There's my degrees of unsaturation. So that's one way you can do it. You can count the pairs of hydrogens. You could just take the number of hydrogens for the saturated hydrocarbon with that many carbons, and then subtract the actual number of hydrogens, divide that by 2, and you'll get the degrees of unsaturation. But you can see here that benzene is highly unsaturated. Okay, so this is something that you'll want to be able to do. Another thing you'll want to be able to do, of course, is to name things. All right. And so when we're naming things, we're going to name longest chain that contains double bond. And we'll start numbering. At end closest to a double bond. And then we'll indicate that number, we'll indicate the position of the double bond of start of, I'm just going to abbreviate double there, DBL. And then we'll number things and name substituents as we did before. So we'll say name substituents as with alkanes. All right, so let's go ahead and maybe take a look at an example or a couple of examples here. So let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. We'll put that guy there, put that guy there, and we'll put that guy there. And what names do I have here? Well, I've got 1, 2, 3, 4, 5 carbons, so that's pent. And I'm going to start numbering at the end closest to the double bond. Okay, so that's carbon 1. So this would be 1 pentene. All right, again, we're going to use the suffix ene, E-N-E. All right, so we can call it 1 pentene. IUPAC actually does recommend calling it pent 1-ene, which is, I think, looks ugly, but that's just me. Both of these both of these names are IUPAC names. Putting the 1 in between the pent and the actual ene helps differentiate if you have multiple different functional groups. So if you had an alkene and an alcohol, it would be whatever, pentene-all, so it could be pent 1-ene-2-all, something like that, which is a little bit of a pain, but it does keep everything straight. This guy here, of course, 1, 2, 3, 4, 5. This is trans 2-pentene, or trans pent 2-ene. I'm not going to write that down. And then this guy here is cis 2-pentene. And for cis and trans, again, what we want to do is look at, we'll go ahead and draw a line along the double bond, and then we'll look at whether our substituents are on opposite sides, that's trans, or if they're on the same side, that is cis. And we'll talk a little bit more about cis-trans isomerism in just a little bit. Okay, a few more things to note here, a few more examples to work on. And let's see, so we can have, well, let's take a look at something with branches. So let's say we had this. Let's look at a few things with branches. And then, well, we'll look at these and then we'll do some cyclic ones. All right. So here, again, I'm going to find my longest chain, 1, 2, 3, 4, 5, 6. I'm going to start numbering at one end, 3, 4, 5, 6. So this is, well, it's neither cis nor trans, right? Because if I draw my line down here, okay, I have two substituents here, so it's neither cis nor trans. We actually have a different type of nomenclature, which is the EZ nomenclature, which I'll get to as well. But let me really quick figure this out. This is the E 3,4 dimethyl 2-hexene. Okay, my methyls are on carbons 3 and 4. My ene starts on carbon 2, and this one tells me it's the E isomer. And again, we'll talk about that in just a little bit. Now this guy here, you might be tempted to start numbering the longest chain, go, oh, 1, 2, 3, 4, 5, 6, 7, 8. But you would be wrong. The longest chain here is 1, 2, 3, 4, 5, 6, 7, like that. So this is 3 propyl, because this is our propyl group right there, 3 propyl, 1 heptene. So we're not numbering we're not naming it after the longest overall chain, but it's the longest chain that contains the double bond. So that's something important to remember. All right, let's take a look at naming cyclic alkenes. So naming cycloalkenes. So we'll start numbering carbons in ring at one end of double bond. Go around in direction of double bond. So if we had something like this, I would number 1, 2, 3, 4, 5, 6. This would actually just be cyclohexene. Now, if I had something like this, well, now I'm going to start numbering, and I'm either going to number 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So I'm going to go 1, 2, 3, 4, 5, 6 in this case, because I need to start numbering at one end of my double bond. So that's carbon 1. Carbon 2 is the other end of the double bond. And then I want to go either clockwise or counterclockwise such that I get the lowest numbers for my substituents. So this becomes 3-methyl cyclohexene. And you don't have to indicate that it's like, you know, 1 cyclohexene or cyclohex-1-ene, because by definition we're starting, the double bond starts at carbon 1. Okay, so otherwise you're naming the substituents like you did before. You can have cis and trans referring to the substituents. You're only going to have cis or E or Z because you can't get a trans due to the ring strain. So you never bother, you know, talking about what is whether this is, you know, cis or not, because it just it is based on the geometry of the molecule. Okay, so let's take a look here, maybe at some more examples here. Some more examples of nomenclature. So these are dienes. They have 2 alkenes. They are dienes. So I'm going to start numbering the straight chain one at one end closest to a double bond. So this would be 1, 3-pentadiene. And that's because my first double bond starts at carbon 1, my second double bond starts at carbon 3. This guy here I could number 1, 2, 3, 4, 5, 6, and this would be 1,4-cyclohexadiene. Okay, I have to start numbering at one end of a double bond. I go to the other end, and then I keep going around. So in this case, my double bonds start at carbons 1 and 4. So if you're going to name some kind of diene, or the same with the triene, etc., you would go ahead and do it in this manner. Now let's take a look at cis-trans for just a little bit here. And so if we have alkenes, we can have quote-unquote free rotation about single bonds. And that's, remember, our Newman projections. We've got staggered, we've got eclipsed. So there's an energy cost to going from here to here, right? But in reality, these guys can twist around, and the energy barrier is relatively small. Sorry, that should be alkanes. Alkanes have free rotation. Alkenes do not rotate about double bonds. Must break double bond to rotate. And so specifically, it's the sigma bond that we can rotate around. So here's our sigma bond, and we can rotate around that. If we have a double bond, remember, a double bond is made up of one sigma bond and one pi bond. So these are just the two phases, the two lobes of the pi bond, but it's one pi bond. And so we can't rotate this. If we wanted to rotate it, we would actually have to break the pi bond, and now we could go ahead and rotate. But we have to break the bond, and that requires a lot more energy than simply going from a staggered to an eclipsed conformation. So we can't get this rotation. So that means that if we could have some kind of isomerization, it would be very slow. So it's either going to be very slow or requires high temperature, or both. It's slow and requires high temperature. It's still slow at high temperature. So again, remember our cis, if we draw our line down the middle, cis, our substituents are on the same side of that line. And if we draw a line down the middle and it's trans, the substituents are on opposite sides of that line. Okay, now I've done a little bit with the cis and trans nomenclature, but what if we had something that was neither cis nor trans? So we can see how you can't do this easily. So of course we have to name things cis or trans, but sometimes we can't. So that's where the E and Z system comes into play here. So let's say we had the following. Let's do this. Okay, and I did this one before. What was this? This was E. Well, no, I didn't do exactly this. This is E. Number 1, 2, 3, 4, 5. So this is E3 methyl 2-pentene. Now, how do I know that? Well, what we want to do is we will draw our line like we did before. But, so let's say draw imaginary line like in cis trans. Look at C's at each end of double bond separately. And then assign priority to each group attached to a carbon, let me see, at end of double bond. And we'll say do for both ends. I'll have to change the con in gold prelog system. So we'll draw our imaginary line, we'll look at each carbon individually, and then we'll assign priority to each group attached to the carbon. And we'll use the con Ingold prelog system. What was that? Well, that was from when we did the R and S nomenclature. So I'm going to look at this carbon here, and I'm going to draw in my hydrogen. And so I have hydrogen as one group, and that CH3 is the other group. So this is my higher priority, and this is my lower priority. Now over here on this other carbon, I have CH2, CH3, and I have CH3. So carbon, carbon, that's a tie, so I have to go one more. I've got 2 hydrogens and a carbon. Here I have 3 hydrogens, so this is my priority, highest priority, and that's my lowest priority. So if our highest priority groups are trans, that is called E. And if the highest priority groups are cis, that is Z. And I have some really bad mnemonics for remembering this. So if you decide to talk with a really bad French accent, you would say that this same, Z and this. Yeah, I know that's really bad. I do apologize for that. So Z, same, so Z, same kind of sounds anyway. These are German E is for I think it's Alkene, which is opposite, I believe, or odd. But anyway, so if our highest priority are trans, it's going to be E. If they were cis, which it's not in this case, it would be Z. So this is going to be, because our highest priority are trans, that's E. And then when I'm actually numbering these, and let me do this, maybe I'll do this in this green here. 1, 2, 3, 4, 5. When I'm actually naming it, I have to name the whole chain. So when I'm just figuring out E and Z, I can focus just on the double bond and what's attached to it. But when I'm actually naming it, I have 5 carbons, so this is a pentene. So this is E, and that's 1, 2, 3. That's carbon 3 has the methyl. So E3 methyl 2 pentene. Okay, so remember, these red numbers here were just for the priority. These green numbers, light green numbers, are the actual numbering of the carbons for the nomenclature. So go ahead and give this a try. There are some practice problems, end of chapter problems. I've posted also the solutions for the end of chapter problems from the Student Solutions Manual, including previous chapters. You can go back and look at those. I don't have a specific problem set for this chapter, so you'll have to rely on those end of chapter problems. But there are a bunch of nomenclature ones, and so you'll want to practice those. All right, so we have gone through all of those topics. It went a little bit longer, I think, than I was originally planning, but we did get quite a bit done. In the next few videos, we'll start looking at some reactions of alkenes, and we will go from there. You'll have to bear with me a little bit because actually my hand has been bothering me as of late, so writing a bunch takes a little effort. So I'm going to try to get these videos out for you guys as soon as I can, but just bear with me. All right. Until next time, stay safe out there. Bye now.